Hi everybody, welcome back. So up to this point in our discussion of Jupiter, we have discussed the general characteristics of the planet and also mentioned the fact that it has lots of moons. We also very briefly touched on the point that it has rings, and that's one of the often unnoted features of Jupiter. That Jupiter actually has 4 main rings. And these these rings are basically formed as a result of interactions between Jupiter's magnetic field and dust particles and Jupiter's moons Metis and Adrastea, which are in the process of getting pulled apart, and Jupiter's moons Amalthea and Thebe, which are in the process of getting hit with micrometeoroid impacts, but which don't have enough gravity to hold on to those particles after they get hit, and those end up going into orbit as a ring. So let's take a closer look at these. Here is a picture of Jupiter's ring system. It's a highly overexposed image taken by backlit imaging when the Galileo spacecraft was behind the Jupiter system. So if you significantly overexpose the image, you can see Jupiter's main ring, as well as maybe hints of its halo ring right in here. So here's a diagram of the system. So you have the halo ring, and then you have the main ring, and then you have these 2 gossamer rings, whose origin we'll discuss very shortly. So first, the halo ring. This is the thickest of Jupiter's rings. It's also the faintest in terms of its, or at least it's the most diffuse of the rings in the area. At least it's a lot more diffuse than the main ring. And this is associated with Jupiter's magnetosphere, which excites dust particles that are in the area into energetic orbits, which is why the ring is so thick, because the magnetic field there is relatively large, and the particles themselves are going to be on somewhat random trajectories. So here is a picture of the halo ring in a highly overexposed image of the Jupiter ring system, and in that below that you can see the main ring just in comparison. But if you significantly overexpose this, which is already overexposed, then you'll be able to see the very diffuse halo ring. Now the main ring. The main ring is a bit more important physically speaking, at least from the standpoint of the physics that is understood by typical students taking this class. This is formed by material coming off of the surfaces of the moons Metis and Adrastea. The idea is that Metis and Adrastea are getting just inside of what we call the Roche limit. Remember, the Roche limit is the area outside of which a moon will be able to hold itself together by its own gravity, but inside of which tidal forces will start to pull the moon apart. In fact, this limit is really only dependent on the density of the material composing the moon. It's not dependent on the size of the moon, because even though the force of gravity is a 1/distance squared force law, the amount of material that an object has goes as its size cubed. So working those out, you realize that the amount of material, that the force of gravity on an object is directly proportional to its radius if it has a constant density. Well, the tidal forces acting on an object are proportional to the size of the object. So there we go, those parts cancel. So it's just that the only thing that really matters is the density. So for a given density, there's a certain distance from a planet that an object of that density will start to get pulled apart if it's inside of that distance, pulled apart by tidal forces. So anyway, in the case of Metis and Adrastea, these 2 moons are within that limit, the Roche limit, and they are in the process of getting pulled apart and turned into rings. We will have more to say about this process when we talk about Saturn, because that actually is how Saturn's main ring was formed, most likely. So here are some pictures of it, and very low resolution images taken by the Galileo spacecraft back when it was in orbit around Jupiter from 1995, I think, until about 2003 or so. And so still, you can see that these are very small moons. If they were significantly larger, then their gravity would have rounded themselves into spherical shapes. And here is a picture with a lot of noise in it of the main ring with one of those little moons there. And I can show you a little video of this. So here's a highly overexposed view of the inner moon Metis, shepherding the inner edge in this case. And then here comes the outer moon Adrastea, shepherding the outer edge. So as these moons are getting pulled apart and kind of helping to create this ring, the gravity of the moons themselves is helping to keep the rings themselves in a nice well-defined shape. So we call these shepherd moons. Now, for Jupiter's so-called gossamer rings, they have this kind of well-defined cutoff structure, and that's hence the term gossamer on this, like something that's been carved in metal. And these are the outer rings. Now, unlike the halo ring and the main ring, these end suddenly. So they have that concave structure at their edges. And the reason for this is because of Jupiter's moons Amalthea and Thebe. Now, the thing is, these moons are, at least for their composition, outside of the planet's Roche limit. So they're not in the process of getting pulled apart. But nonetheless, they're associated with these moons. That was noted by the fact that their thicknesses and edges correspond with the perigove and apogee of those moons in their elliptical orbits around Jupiter. So what's going on here is, even though they're not getting pulled apart by tidal forces, they have such weak gravity that whenever a little meteorite impacts the moon, it ends up spraying up particles, and these particles are not going to be able to be kept in by the gravity of that moon. The tidal forces are large enough to pull off particles that have already been ejected off with some velocity. And even if that's not the case, a lot of times the particles get ejected off at the escape velocity from those moons. So the result is that you end up getting these kind of ring clouds that correspond to the orbits of these moons. So the top picture is the actual infrared observation of these rings from the Galileo spacecraft, and the bottom picture is a computer simulation of about what they should look like. So at least in terms of the shape, there's a very nice correspondence there. So here is a picture of Amalthea. A little bit of trivia for you. Amalthea is the last moon in our solar system that was discovered by direct visual observation. It was discovered, I think, around like 1891, or at least early 1890s, by Eugene Barnard, and he saw it through a telescope. It's like, oh, there's this little dot around Jupiter. What's that? And since then, all moons have been discovered based on photographic plates. In other words, you expose the image for a long time, and you look to see if there's anything there. And in fact, most likely this moon will always hold that record because of the fact that nowadays we use high technology with very good photographic techniques with CCDs to significantly expose and continuously gather light to see things that our eyes would have no chance of seeing even when looking through the world's biggest telescopes. Here's a picture of Thebe, the progenitor of the outer gossamer ring. So a quick summary of how Jupiter's rings come about. So it's really Jupiter's magnetic field and tidal forces and meteor impacts that are the three main agents that cause Jupiter to have rings. The halo ring is formed by particles being thrown around by Jupiter's magnetic field. The main ring formed by particles being pulled off by tidal forces from the moons Metis and Adrastea. And the gossamer rings are formed by particles being ejected by meteor impacts and then captured by Jupiter's gravity. So here is a nice picture of that. So you expose the picture of the main ring and then significantly overexpose it, and then you start getting the gossamer rings coming in. And notice you can also see the halo ring. So actually the gossamer rings are a bit fainter than the halo ring, though the halo ring itself is significantly fainter than the main ring. And here again, you can see a nice little picture of one of the shepherd moons around Jupiter's main ring. Now, before we end our discussion of Jupiter the planet, we do want to mention a few more things. So in terms of future missions, The Juno spacecraft is currently in orbit around Jupiter. It's been gathering lots of data. This is the spacecraft whose data has allowed us to discern that Jupiter's core is most likely at least partially dissolved into the lower part of Jupiter's metallic hydrogen mantle. And the spacecraft is going to continue in orbit around Jupiter, I think, for at least another few years. The European Space Agency plans to launch the Jupiter Icy Moon Explorer in the year 2022 to explore Europa, Ganymede, and Callisto, and that'll arrive in the year 2030. And also there is the Europa Clipper mission, but we'll have more to say about that when we talk about Jupiter's moons, because the Europa Clipper mission is meant mainly to investigate Jupiter's moon Europa, and it should drop a lander, but that has not yet been launched by NASA. Now, one more thing, something to think about. An extrasolar planet with the very awesome name of SIMP J01365663 plus 0933473 was discovered in 2016, and it has a mass 12.7 times the mass of Jupiter. So that kind of puts it at the upper threshold of what you can call planet, and anything much more massive than that is going to be a brown dwarf star. So it was recently found using a radio telescope, the VLA, the Very Large Array of radio telescopes in Socorro, New Mexico, that this planet has significant aurorae, which are likely caused by a magnetic field that's 200 times stronger than Jupiter's magnetic field. Now, you know that aurorae on Earth and a lot of Jupiter's aurorae come from the interaction of solar wind particles with the magnetosphere and then interacting with the upper atmosphere of the planet, producing all kinds of colors due to those interactions. There's one problem, though. This extrasolar planet, SIMP J yada yada yada, isn't actually orbiting a star, so there's no stellar wind. So what particles are getting trapped by this planet's magnetosphere? How is that happening? Where are these particles causing these aurorae coming from? So here's kind of an artist's visualization of this, and I'll give you a hint. This video has given enough information by itself to allow you to come up with an idea of this. In fact, it is the dominant idea in the scientific community of why this planet has aurorae. So if you need to think about it for a little bit, maybe pause the video, but I'm going to tell you the answer in 5 seconds. 5, 4, 3, 2, 1. Okay, this planet almost certainly has a moon orbiting around it, and this moon either has processes that are ejecting particles, like Io's volcanic aspects, or are getting emitted because either it's getting pulled apart by tidal forces or getting hit by meteorite impacts, that sort of thing. So yeah, this planet has a moon that is sloughing off some particles that are getting caught up in the planet's magnetic field, and then end up getting drawn toward the polar regions and creating aurorae. So that is the answer. Okay, so I hope this video on Jupiter's rings and some of the associated aspects of it, and just rounding off our discussion of Jupiter, was informative. Questions and comments in the comment section on YouTube. And hope to see you next time when we start talking about Jupiter's moons in more detail. Thank you.